Section 5.3 deals with graphs of polynomial functions. So what I'm going to talk about next is a little different than what we have looked at before. So you can tell something about the roots of a function by how the curve passes through the x-axis. For example, it might pass straight through. So if it passes straight through, then that gives us just a single zero. Or you could have this where it kind of bounces back. And if it bounces back, then we say that has a zero with multiplicity of 2. And I'm going to show you an example of how that looks as far as your polynomial. Or you might have something, and we're going to describe this as a wiggle, where it kind of is, you can see it's increasing, and then it kind of has a little bit of a wiggle and a turn, and then it turns and goes this other direction. That is a zero with a multiplicity of 3. So and I'm going to go ahead and I'm going to come back to this in the gray box, but I'm going to go to this one instead. So looking at this polynomial function, and we're told that it's a polynomial function of degree 6, and we're asked to identify the zeros of the function and their possible multiplicities. So we have 3 zeros. So I'm going to make a little table. I'm going to have my zeros, and I have my multiplicity. So I have a 0 at -3. The zeros are just the x-intercepts. I have a 0 at -1, and I have a 0 at 4. At -3, it's a bounce back. Okay, you can see it turns there. So because it's a bounce back, if you look here, that's a multiplicity of 2. So I'm going to list that as a multiplicity of 2. At -1, it passes straight through. It almost looks linear, passes straight through. So that's a multiplicity of 1. And at the 4, we have a wiggle. And if you look back here, that's a multiplicity of 3. Now, when you are, some of the things up here, and I'll talk about this, if the graph crosses the x-axis and appears almost linear at the intercept, it's a single zero. So that's my -1. If the graph touches the x-axis and bounces off of the axes, it's a 0 with an even multiplicity. It doesn't have to be a 2. It could be a 4 or a 6. In this case, it's a 2. I'll tell you why in a minute. If the graph crosses the x-axis at a 0, it is a 0 with odd multiplicity. This is the wiggle one, so this was right here. So that wasn't really said very well, I don't think. And then the sum of the multiplicities is in. So in this case, if you notice, the sum of our multiplicities is 6. So that's the reason why I know that even though this bounce back has to be an even multiplicity, I know it has to be 2, because if it were a 4, 4 plus 1 plus 3 is too big, because we were told that this had a degree of 6. So I know that this has to be the multiplicities for these. And actually the same thing with the wiggle, the one here, it has to be odd. It doesn't have to be it doesn't have to be a 3, but in this case it did, because otherwise it would be too big. So what does that mean? Remember that if -3 is a 0, then x plus 3 was a factor. And if -1 is a 0, then x plus 1 is a factor. And if 4 is a 0, then x minus 4 is a factor. Well, the multiplicities tell you that this x plus 3 would have to be squared, the x plus 1 would be to the first power, and the x minus 4 would be cubed. And this would be my polynomial. So I'm going to call this p of x for polynomial, with the exception, and I'm going to put a value of a right here, there might be some kind of a stretch or compression, and we don't know that. That's one of the things we're going to be looking at, but we didn't need to here because we weren't even asked to do this. We were asked to identify the zeros and their possible multiplicities. So our zeros would be -3 with a multiplicity of 2, are -1 with a multiplicity of 1, and 4 with a multiplicity of 3. Now, if I go back to this previous gray box, that's just what it was talking about here. If a polynomial contains a factor of the form x minus h to the p power, the behavior near the x-intercept, h, is determined by the power of p. So that's just if p is 1, it's the straight through. If p is 2, it's a bounce back. If p is 3, it's that wiggle. And we say that x equals h is a 0 of multiplicity p. The graph of a polynomial function will touch the x-axis at zeros with even multiplicities. The graph will cross the x-axis at 0 with odd multiplicities. And the sum of the multiplicities is the degree of the polynomial function, so which is kind of what we went over on this. All right, so that's kind of the idea, that idea of multiplicity. We've seen things like this before, but we haven't really talked about the zeros in those regards. So, looking at an example, things that we need to know the end behavior, we need to know the x and y intercepts, and we need to know the multiplicities. Well, we talked about end behavior in the last section. Notice that the highest power is a 3, and it's positive. So this one, the end behavior, is going to go something like this. Now, we don't know, it could have a couple twists and turns in between, but we know that the end behavior looks like this, and we can say as x goes to infinity, f of x goes to infinity, and as x goes to negative infinity, f of x goes to negative infinity. So that's our end behavior. I'll put a 1 there. Our intercepts. Let's do our y-intercept first, because that's super easy. You just evaluate f of 0, and when you plug in a 0, you get 0. So my y-intercept is 0, 0. To get my x-intercept, I'm going to have to factor this. So actually, I want to set this equal to 0. So let's start by saying x cubed plus 6x squared minus 7x equals 0. Always start with GCF factoring first, so I get x times x squared plus 6x minus 7 equals 0. And then you can do a diamond problem here, and we're going to end up with a positive 7 and a negative 1, because the outside would be a negative x, and then a plus 7x gives you the plus 6x in the middle, and then you have a negative 7. So my zeros, x equals 0, x equals negative 7, x equals 1. And our multiplicities, multiplicity of 1, and I'll just say each. Okay, notice we have a third degree. We have 3 zeros. Each of them have a multiplicity of 1. When you add up the multiplicities, you get the degree of the polynomial. So then we're asked to graph. So when you graph this, okay, that was not very good. We're going to start by plotting our zeros. So we have 0 is one of them. Negative 7 is one of them. I'm counting by ones on the x-axis anyway. And 1 is one of them. Our y-intercept we said was 0, 0, so we don't have a separate thing to mark there. So it's kind of hard to tell how high up. If I were just going to do a sketch, now pay attention to the end behavior. I know the right end's up and the left end's down, and it has to pass through here. What you might want to do is just check and see, well, what's going to happen between 0 and 1, and what's going to happen between 0 and negative 7. So it's fine to get your graphing calculator out to kind of help you out with this. So plot that, or go ahead and put the equation or the function into y1, and then set up your table, because we're going to look at the table. And it doesn't really matter where you start at, but I'm going to go in increments of a half because I want to know what's happening between 0 and 1. Set it up to auto and auto. And then when you go to your table And notice that between at 1/2, I'm at negative 1.875. So, and before I plot that, let's go up and see what happens between 0 and -7. So you can see that the numbers are getting really high. It looks like at negative 4.5, that might not be the maximum because we don't know what's happening on either side, but we're going to use that because we're just going to kind of approximate with our calculator. So so then if I need to go up to 61, I'm going to count by tens. So at negative 4.5, I need to be about 61. And again, I'm just kind of approximating. I guess I should have stuck with my red since I was doing that. And then in between the 0 and the 1, I forgot what it was. It was negative 1.875. So remember, if this is negative 10, so it's not very far down. So then we can graph something that looks like this. It's going to come up through here. It's going to come down through here and then go up. So that's just kind of a rough sketch, but notice the end behavior. So I'm kind of using my calculator to get, to see approximately how high up it goes. And so now I have a fairly accurate sketch of that problem. Okay, so let's try the next one. So notice that this is an even degree polynomial. So as x goes to positive or negative infinity, I can put this statement together now. F of x, since it's positive 1x to the 6th, goes to positive infinity. All right, so both ends up. And it's going to do some twisting and turning in the middle, but we know that the end behavior is going to be something like this. And it could twist and turn in the middle, but the end behavior both ends up. The second one, I'm going to do the y-intercept first again. So g of 0, we get 0. So 0, 0 is my y-intercept. To get my x-intercept, I'm going to let this equal 0. Again, GCF factoring first, I can pull out an x squared, and I'm left with x to the 4th minus 3x squared minus 4. All right, now this is going to be a little tricky step right here, but we've talked about this before. I think I'm going to come up here and do this problem off to the side. This x to the 4th minus 3x squared minus 4. This is called quadratic form. We did that earlier this year, and we did it last year as well. So because this is an x squared and this is x to the 4th, notice that the power is twice as big. So this was where we said let u equal x squared, then u squared is x to the 4th. So you can think of this as u squared minus 3u minus 4. Factor it with a diamond problem. And we have a negative 4 and a plus 1. And then just remember, it's not really a u. Then you can go back. It was an x squared minus 4 and an x squared plus 1. So now I'm going to go back down here and say this was x squared, and this factors to x squared minus 4 times x squared plus 1. All right, almost done, except x squared minus 4 is the difference of two squares. So I have x squared, x plus 2, x minus 2, and x squared plus 1. That's a lot. So my zeros, x equals 0, x equals negative 2, x equals positive 2. the x squared plus 1 equal to 0 doesn't have a solution. So because that would end up with a complex solution from that part. Okay, so I'm going to count by ones on the x-axis. So I have a 0, at -2, and at 2. Now when we look at these, the 0 has a multiplicity of 2 because it's squared. So this has a multiplicity of 2, and these both have a multiplicity of 1. Okay, now you might go, well, how come it doesn't add up to 6? Because this one had complex as well, imaginary, so that's why it doesn't. Then we know the end behavior goes up, and so it's going to come down and then come back up and then bounce back at the 0. So if we didn't care about the vertical scale, I could just draw that in. But if we wanted to kind of get a little bit more accuracy, type that in. I went to the table set. I left it in increments of 1/2. And we can see that at -3, it's going to be really high up. We're not going to kind of plot that one. I'm really interested to see in the in-between. So at -1, it's at -6. So I could plot, let's see, I want to go down as low as about -12.8. So you could count by probably by 2s. So -2, -4, -6, -8. -10, -12. So then at -1.5, we're at about a -12.8. So I'm just going to kind of approximate there. You can see that 1.5, because it is symmetrical. So at 1.5, it comes down to about here. So that's enough now that we can see it's doing this, because it goes straight through, comes back up, bounces back at the 0, because that had a multiplicity of 2. And notice the end behavior. Okay, so we get our 0s because those are like anchor points. We know it bounces back at 0 and passes straight through at -2 and 2 because of our multiplicities. And then we just used our calculator to find how far down we needed to go and how we needed to scale our graph. So for our next one, to factor it, well, first of all, let's do our end behavior. As x approaches infinity, f of x also goes to infinity because the right side's up. And as x goes to -infinity, f of x goes to -infinity because that side's down. So it's going to do something like this. Right side up, left side down, like the parent graph. All right, so then finding our 0s, if we find our y-intercept, if we plug in a 0, h of 0 gives me a 0 plus 0 minus 0 minus 18, so it's -18. So this time my y-intercept is 0, -18. And to get my x-intercepts, I need to set x cubed plus 2x squared minus 9x minus 18 equal to 0. There is no GCF to factor out. If you go to your factoring flowchart and you have 4 terms, there was something I said to do on your factoring flowchart, something to try. It doesn't always work, but it's going to here. If you put 1 term in each box, and then you do GCF out of each row, so I can factor out an x squared, which makes this an x, which makes this a plus 2, which makes this a minus 9. So I get x squared minus 9 times x plus 2 equals 0. X squared minus 9 is the difference of 2 squares, so I get x plus 3 times x minus 3 times x plus 2 equals 0. So my 0s are x equals -3, +3, and -2. All of these have a multiplicity of 1. We don't have any complex ones in this one, and notice that 1 plus 1 plus 1 is 3, and we had a 3rd degree. Well, unfortunately, my calculator just froze up, and I can't fix it without messing up the video. So we'll go without. So on this, we're going to plot our zeros. So we have -3, +3, and -2. And I know I can plot my y-intercept of -18. So I'm going to count by 5s. So my y-intercept is here, and that helps a little bit because I can see, I know the end behavior, so I know that it must start far lower down and then come up. I just don't know how high up. I'm just going to tell you, and I don't have the number written down, so but I had the work done ahead of time. So it's about here, and if you plug in to get kind of the lowest point, it goes down as far as about -24, I think it was around here. So you could do that on the calculator and come up with those values. So we end up with a graph that goes something like this. Okay, and I guess I could have got my calculator that's not on the video and used that to come up with those numbers. But so roughly it's going to look something like that. But notice the end behavior we've already thought about. We plot our zeros, those are anchor points. The y-intercept can be an anchor point. I mean, sometimes it's not, doesn't add any more information if it's a 0, 0. All right, so on the next example, notice it's already factored. So my zeros, I have a 1 with a multiplicity of 2. I have a -2 with a multiplicity of 1, and I have a 3 with a multiplicity of 3. So that tells me about the behavior. Is it going to bounce back? Like the 1 will bounce back, the 3 has a wiggle, the -2 passes straight through. Then I also know that this has an x squared times an x times an x cubed. So my leading coefficient, if you add the exponents, is going to be x to the 6th. So this is going to be an even degree polynomial, which means, and it's positive, so both ends up. Notice I didn't bother even multiplying out the whole thing because I really don't need to. So I know that as x goes to plus or minus infinity, f of x goes to positive infinity because both ends are up, because it's an even degree polynomial. So I'm going to plot my zeros. So I have a 1, I have a -2, and I have a 3. So there's my zeros. And so what's going to happen when we do this is, remember, it passes through. I'm actually not going to scale it vertically. So, but it's going to come down through here, and it passes through, and then it's going to come back up and has to do a bounce back through here, because remember, that's a bounce back. So then it's going to have to come down, but then it has to do a wiggle. So that was not very good. Okay, it's not the greatest, but you should check that out on your calculator. Let me see if I can do better. It's more like that. When it does this little wiggle thing, it changes concavity. This is concave down, like a frown right here, and then it switches to concave up, and that's actually also a point of inflection, but that's kind of what, when you have that little bit of a wiggle. But I didn't put a vertical scale on there. With your calculator, we could have done a little better. So what we're doing next is we're given a graph, and we actually have to find an equation. And notice it says, be sure to find the leading coefficient. So I'm going to start by listing my zeros. So my zeros are -4, -2, and 1. The -4 has a multiplicity of 1 because it passes through. At the -2, it passes through. But this one has a bounce back, so it's a multiplicity of 2, or it's an even multiplicity. So now for my polynomial, and I'm going to call this p of x, I know that I'm going to have x plus 4, because remember, if negative 4 is a 0, x plus 4 is a factor. I have a factor of x plus 2, and I have a factor of x minus 1, and that has to be quantity squared because it had a multiplicity of 2. What I don't know is there must be some value here for that, and I have to solve for that. That's going to be my leading coefficient. So now what? Well, what you're going to do next is find a point on the graph, but that's not one of the zeros. What you don't want to do is multiply all this out. Don't do that. Okay, so it looks to me like the point 224 is on the graph. So I'm going to use 224. So if I plug a 2 in for x, then p of x is 24. So I'm going to have 24, that's like my y value, equals a, 2 plus 4, 2 plus 2, 2 minus 1 quantity squared. Okay, so I am just going to solve this. I get 6 times 4 times 1 squared is 1. So 24 equals 24 times a. Dividing by 24 gives me a equals 1. So then I don't need it. So there is no stretch. So I can just say my answer is this. And you do not have to multiply that out. You can leave it in factored form. So next problem, my zeros are negative 1 with a multiplicity of 3 and 3. So this has a multiplicity of 3, and here we have a multiplicity of 2. So we have p of x equals, I don't know what my leading coefficient is. I'm going to have x plus 1 quantity cubed, x minus 3 quantity squared would be my function. So now I'm going to find a point on this graph that I think looks like it's on there. And I think I used, what did I use before? Okay, I was thinking that this looked like negative 2, 12.5, and I actually used that. So we would have 12.5 equals a, and if I plug a 2 in for the x, then I'm gonna write it out. So I have 12.5 equals, I'm gonna have 3 cubed, so 3 cubed is 27, and negative 1 squared is a positive 1. So then I end up with, wait, I did something wrong. That's supposed to be a negative 2, sorry. Rewind. Actually, there's no rewind. So I have 12.5. Here I get a negative 1 and a positive 25. So I have negative 25a. So when I solve for a, I'm going to divide by negative 25. I get negative 1/2. So that means my equation, p of x, is negative 1/2 x plus 1 quantity cubed times x minus 3 quantity squared. Now I want to check out the end behavior. Notice that this time the left end is up and the right end is down, and that's confirmed with our value, with our leading coefficient being a negative. That makes sense. Okay, on the next one, I only have 1 0, so that's at 1 with a multiplicity of 2. So we get p of x equals a times x minus 1 quantity squared. Well, that looks kind of familiar. So notice that if I look at my graph and I go over 1, I go down 1 from the vertex. And if I go back to the vertex and I go over 2, I go down 4. So over 1, down 1, over 2, down 4. That means it's not stretched, but it's going down instead. So P of x equals -1 or negative x minus 1 quantity squared. So I could just use what I know about graphs. I could have picked a point and done the same thing. I could have picked -1, -4, plugged it in and solved for a, and I would have got -1. All right, next one. Our zeros. We have a -3, a 2, and a 4. Passes through, passes through, passes through. So all multiplicity of 1. So P of x equals a times x plus 3 times x minus 2 times x minus 4. So then if I pick a point on the graph and I used the y-intercept, 0, 48. So then 48 is the y value. 0 plus 3 is 3. 0 minus 2 is -2. And 0 minus 4 is -4. So -4 times 3 is -12 times 2 is a positive 24. So A is 2. So P of x, P is for polynomial, is 2 times x plus 3 times x minus 2 times x minus 4. And one last problem. Our zeros are -4 and 0. This has a multiplicity of 3. I know that all we know is that it's an odd multiplicity. We're going with the least possible degrees. And the 0, this looks like it passes straight through, so I would say that's a multiplicity of 1. And we have P of x equals a times x plus 4 to the 3rd power times x to the 1st power. So then I have to pick a point on my graph. And what did I pick? I think this one right here appeared to be -6, -48. Right here. So if you plug in a -48 for the y value and a -6 here, so we have -2 cubed is -8 times -6. So it looks like we get a equals -1. Both ends down, so that makes sense. So then P of x equals -1. I'm just going to put a negative. I'm going to bring the x to the front because that's normally where we see it. X plus 4 quantity cubed. And I know that was a lot, but we got through it all. And that wraps up your assignment for today.